Part 1, trees and print tree. So we'll start with the data structure of a tree. A tree data structure, according to Google Images, looks like this. You have a root, and these are called nodes, and nodes can have what are called children, and children have a parent. So B is A's child, and A is B's parent. Okay, and every node has exactly one parent, but a parent can have multiple children. This is all labeled right here. The children are called siblings. So far, so good. The one at the top is called the root. And then if you have no children, you're called leaves. Those are leaves. Okay? That's a tree data structure. In a binary tree data structure, you have every node can have only up to 2 children. You can have fewer than 2 children. For instance, the leaves here they'll have no children. And in this one, this node right here only has 1 child. Okay? But you have a left child or a right child, or a right child. So that's a binary tree. Okay? So we could represent a tree, and we're going to do a binary tree in a list, because we don't know about object-oriented programming yet, and there are nice ways to represent recursive data structures as objects. But what we're going to do instead is we're going to say a tree, for example, might look like this. This would be the tree that just says A at the root. Okay? If we look at a tree here, let's look at that tree right there. Okay, A, B, D, C, E, F. So A at the root. Now every node can have 1 or 2 children. Well, 0, 1, or 2. So this one can have A and B as its A can have B and C as its children. So we'll do a tree as a value followed by its left child followed by its right child. Okay? So the left child here in this picture is B. You might think it's B, but it's not really, because the left child, if you look at it, is really a tree. Okay? It's not just B, it's an entire tree with B and a child of D. Okay? So if we just look at that, if we look at the bottom here, just that D, we're going to build this bottom up instead of top down. That tree D is this tree right here. Oops, that's the tree just D, no children. Okay? The tree here rooted at B would be a tree at B whose left child, let's actually put this over here, that's how we should do this, whose left child is in fact that tree D, and whose right child is none. And by the way we're going to do it, if you don't have a child, you just leave it off. So this tree has a root of B, that's there, a left child of the tree that has a root of D, and nothing else. Fine. And this entire tree is in fact the left child of A. So it'll go right there. Excellent. Okay? Now on the right-hand side, maybe we can do this without all that discussion. C, left child is the tree E, right child is the tree F. Okay? So this is a list composed of lists, where at each level, we're going to say basically each node, each value in the tree is a value followed by child 0 and child 1, where we can omit these if they're not there. Child 0 and child 1 themselves are of the same form. Great. So now, if that's a tree, what we want to do is we want to write a function to print a tree. So we're going to call it print tree. It'll take a tree as we just defined, and what we want to do is we want to print it like so. Okay. We want to, for this tree, we'd want to print A, B, D, C, E, F. So this says that it has a node A, left child is B, B has a left child of D, B has no right child. Then back at the A level, the right child of A is C, whose left child is E and right child is F. I hope you can see how this is the same representation, is a representation of that tree. And we want print tree to take the tree and generate this output. So how do we do it? Well, we're going to do it recursively, something we haven't actually learned yet, but what the heck, let's do it. So to print a tree, you simply print, you need to know its value is tree of 0, right? Because let's have this comment here for our code up here. Okay, value is tree of 0. Its child 0 is tree of 1, but remember that could be optional. So if len of tree is greater than 1, say greater than equal to 2, put it that way, else none. And then child 1 would be tree of 2, 0, 1, 2, but only if there is a tree of 2, otherwise it's just none. Okay, cool. So now we have the value and the children. You want to print the value, and then you want to print the children. So you think you might want to do something like this. This looks actually not bad. Let's call it print tree of tree, where of course our tree is that tree down there. Let's when we run this, we see it printed the A, and then when it printed child 0, it printed B, D. But here's the deal. We really wanted to print that entirely as a tree, and that's where the recursion comes in. Print tree of child 0 and print tree of child 1. So you print the value at this, and then you recursively print the entire child. Now, when you do that, this is actually going to recurse forever in Stack Overflow or crash in some other way. We have to think about how this ends, because you print this child, but to do that, it prints this child. There's two cases where it ends, but basically it ends if I don't have a child. So if child 0 is not equal to none, I'll only print it if it's there. And if child 1 not equal to none, I'll only print that if it's there. Okay. Now when I run this, cool, it printed A, B, D, C, E, F. So it prints all of them. But it's hard to keep track of the structure here. Like, is B a child of A? Is D a child of B or A? And for that, we're going to use indenting. And for indenting, we have to know the depth that we're at. The outermost depth will be depth 0. But then when we recurse, we'll add 1 to our depth. As a consequence, we'll know that B is at depth 1 and D is at depth 2. Then when you print the value, all you need to do is indent by the depth, and there it is. So now we see we have the tree A, B, D, C, E, F, which corresponds A, left child B, left child D, right child of A is C, left child of C is E, right child is F. Bingo, and there's our print tree. So now we know about trees as a recursive data structure that we're representing in lists, and we know about print tree as a recursive function that calls itself to print out that tree data structure. We're going to need this to do the rest of Huffman encoding.